Welcome to the 23rd lecture on digital simulation. In this video, we will see what is artificial ringing in numerical solution of electrical circuits. We will explain this concept with the help of an example. So consider this simple circuit consisting of a voltage source Vs, resistance R and a capacitance C. The values are given here. The resistance value is 1 ohm, capacitance value is 1 millifarad, and the step size used H is equal to 5 millisecond, and this voltage source Vs is having this particular shape. So till 50 millisecond it is linearly increasing, then after 50 millisecond it is a constant equal to 1. Okay, so this is the shape of the voltage applied or source voltage. So let us write the differential equations governing the circuit. So at this second node, at this node, you can write KCL. So the current through this capacitance will be C into d V2 by dt, and the current through this resistance going out from node 2 is V2 minus V1 by R. So the sum of these two currents will be equal to 0, and that is written here. That is this equation: C into dV2 by dt plus V2 minus V1 by R equal to 0. Then after rearranging the terms, you can write the equation like this: dV2 by dt is equal to V1 by RC minus V2 by RC. Now let us write the let us use backward Euler technique to solve this numerically. So in backward Euler technique, we can replace the left hand side with this term V2n plus 1 minus V2n by h. This derivative term is expressed as this finite difference, V2n plus 1 minus V2n by h, and on the right hand side we will calculate this function value at t equal to tn plus 1 in backward Euler method. So this is corresponding to backward Euler technique. So the right hand side of the differential equation will be evaluated at tn plus 1. So that is written here, V1n plus 1 by RC, and this becomes V2n plus 1 by RC. Now after rearranging the terms, you can write an expression for V2n plus 1, that is the capacitor voltage at t equal to n plus 1 the instant. So once you get the value of V2n plus 1, you can easily calculate the capacitor current. Capacitor current at n plus 1 the instant is nothing but same as this current through this resistance, since this is a linear circuit. So current through this resistance is in this direction is V1 minus V2 by R. So IC n plus 1 is nothing but V1 n plus 1 minus V2 n plus 1 by R. So once you get the value of V2 n plus 1 from here, substitute it in this equation. V1 n plus 1 is already available, since it is a source voltage, we already know the value. You can calculate the capacitor current at the n plus 1 instant. So this is for backward Euler technique. If we are using trapezoidal method, then the approach will be different. That also we have studied before. In trapezoidal method, the left hand side is same, dV2 by dt is replaced by V2n plus 1 minus V2n by h, but the right hand side we will replace by half of the slopes, sum of the slopes evaluated at tn and tn plus 1 by 2 into f of tn plus f of tn plus 1. This is the formula for the right hand side. So half into this right hand side evaluated at tn plus 1, that is written here, then plus right hand side evaluated at tn. So if you rearrange this lengthy expression, you will get an expression for V2n plus 1. Okay. V2n plus 1 will be equal to this quantity divided by this constant. So this is the expression for V2n plus 1 in trapezoidal method. Then from that you can calculate IC n plus 1 as I have explained before, like Vn1 n plus 1 minus V2n plus 1 by R. And I have simulated both the cases in MATLAB, and if you observe the results, you can see that in trapezoidal method, in backward Euler method, this is the result. Capacitor current will be initially rising, and then it reaches a steady value. Then at t equal to 50 millisecond, our source voltage is changing, or source voltage changes to constant value 1. Previously it was linearly increasing, now it is a steady value. then at that time the current decreases to 0. So if you observe this waveform clearly, if you observe this waveform, you can see that at the corners of like here, there is some error, because actual solution will be a smooth function of time. So there is some error in this transitions. Why is it so? It is because of the large step size that we have used, because we are using a step size of 5 millisecond, but the R value is 1 ohm and the C value is 1 millifarad. So the time constant of the circuit is only 1 millisecond. So the step size that we are using is greater than the time constant of the circuit. That is the reason for this error. But if you are if you are solving the same circuit with the help of trapezoidal method, you can see that here there are oscillations in the transition periods. You can see oscillations in these two regions, whereas in the backward Euler method there was no oscillation even though there was error. But here there is error and the sign of the error is changing alternatively, positive and negative. So that phenomenon is known as ringing in numerical method. So the observations are there are significant error in both methods due to the large step size used compared to the time constant of the circuit. Because of the large step size, there is significant error. But in trapezoidal method, only in trapezoidal method, not in backward Euler method, the numerical solution oscillates. It oscillates around the true solution. So this oscillation is called a ringing. So now let us see what is the reason for this ringing. If you write the general expression for capacitor current, it is C dVc by dt equal to IC and dVc by dt equal to IC by C. And if we use the trapezoidal rule, you can replace the left hand side dVc by dt by this one, Vcn plus 1 minus Vcn by h, and the right hand side is half of the function evaluated at n plus 1 and n. And if by rewriting you will get expression for Vcn plus 1. Now if you rewrite this expression in terms of Icn plus 1, for Icn plus 1 you will get an expression like this. If you rearrange the terms for Icn plus 1, you will get an expression like this. And here there is an interesting observation. If the capacitor voltage is constant, almost constant, if the capacitor voltage is practically constant, then Vcn plus 1 and Vcn are approximately equal, and this is 0. This term vanishes, and Icn plus 1 is equal to minus Icn. So it has a negative sign. So the n plus 1 value is negative of the nth value. So there is a changing sign. That is the reason for this ringing phenomenon. So this is about artificial ringing in digital simulation. Thank you.